Hi everyone, welcome to our stream. This is a stream for just Physics 102, and I'm only going to look at the wave equation because it involves calculus, and so that's only for the calc-based students. The live stream that I did every yesterday is for everyone. Okay, so it covers all the other stuff. So this live stream, because it's the only calc-based stuff that I did since the beginning of the semester. It's the only thing that is specific for 102. Okay, so let's take a look at this equation. You might wonder what kind of questions could I ask about this? Well, before I jump into the questions, I should give you just a little bit of the theory to remind you about what that equation talks about. And basically what it says is that if you have some amplitude, which I called y here, and it's this amplitude is the amplitude of a wave. It changes both in time and in space. So if you differentiate it twice with respect to time, that's actually going to be the same as differentiating that function twice with respect to space, x, only there's a velocity in there. Okay, so what does it even mean? Well, let's take a look at a picture here. Here's the equation. So the equation up here you could see is d2y by dt squared. That's actually the acceleration. So I didn't draw y in here. Maybe I should just draw y. Y is up this way. Okay, so like that. So, you know, if I had a dashed line in there like this, that dashed line would correspond to y equals 0. Okay, that means 0 height. Okay, and x is this way. All right, and I can't obviously draw time, but you'd have to imagine this thing evolving over time. So this crest here would move to the right. Okay, so d2y by dt squared, basically that's at a fixed point x, because x is not changing in this derivative, but time is. And if you take a look at a fixed point in a wave, it oscillates up and down like that. Okay, if you take a look at this second derivative with respect to x, that corresponds to the shape of the wave. And basically this says that the oscillation of any point in the wave gives rise to its shape. Okay, that's the way to think about it. Now, it's hard to really animate this, but you can imagine that as this bobs up and down, you know, the tail here, it's kind of like, you can imagine like that red spot there is like a pen, and there's like a piece of paper moving to the right here. And as the pen moves up and down like that, it etches out this sine wave like that. Okay, that's roughly what this equation is saying here. Okay, and so what kind of questions could I ask? Well, let's take a look here. So the solutions to this equation are sinusoidal. You could either do sines or cosines, they'll both work. And so basically what I want you to be able to understand is, one, just the fact that this is relating the acceleration here of one point to the shape. Okay, so I could ask, you know, just that you questions to make sure that you understand that, but also just questions to show that this equation here actually leads to this equation right here. Okay, V is equal to lambda times F, like that. Okay, and you might wonder, geez, how in the world do you go from the second order differential equation here to V is equal to lambda F? Okay, and we solve problems with V equals lambda F in the other live stream. Okay, and well, that's what I'm going to show you. Okay, so if you have a sinusoidal here function, it could either be a sine or cosine. We played with the cosine, and it's got to be a function of both time and space. Okay, that's because well, from the diagram you saw a minute ago, the amplitude will change both in time and it'll also change in space. So I'll just show you again here. If you just wait over time, this red spot there, okay, so it's at a fixed x. I mean, like I could just say, I don't know, x is equal to 5 here, like that, 5 meters. I don't know, just pick any old x you like, okay, like that. And you say, I'm going to just look at x equals 5 meters, but I'm going to wait in time. This thing will bob up and down like that, sinusoidally, okay? And that's this part of that function right here. Whoops, that's this part of that function right there, cosine omega t. Okay, well, you should know that because that's the simple harmonic oscillator. But this also has an oscillation in space. Okay, and what I mean by that, it has a shape here, which is a sine shape like that, and that shape there is a sine shape. Okay, and that part of the function is this. Okay, you could see it's also cosine, but now it's cosine of this kx there, like that. Okay, if you plug this into, if you plug y into here, into that function there, and you work through it, you'll actually get this. Okay, so that's what I'm going to go over right now. All right. So the first thing is you have to understand what this omega is and this k. Okay. So omega is known as the angular frequency, and k is known as the wave number. And how is omega related to the linear frequency? Because over here in this equation, I don't have an omega, I have an f. So how does that f and that omega relate? Well, if you imagine that x is fixed and you let time vary, okay, uh, the cosine makes a cycle in 2 pi, okay, so that means in time little t is equal to capital T, where capital T is 1 period. This whole function, this whole value here must equal 2 pi, okay, because it has to go from, like, one complete, well, it's got to go one complete cycle. Like if it starts at the top there, in time capital T, it's got to go to the bottom and then back to the top there. And because cosines do that in 2 pi, you must have that omega times capital T times the period must equal 2 pi. Or if I isolate omega, I get that omega is equal to 2 pi over capital T, and that relates the angular frequency and the period. Okay, but I don't have a period up here in that, so I have to convert from the period to the linear frequency, and that's just 2 pi f, like that. Okay, so f is equal to 1 over capital T, like that. Remember that the linear frequency is related to the period by this formula there. Okay, and so if I just get rid of that 1 over T and I replace it with an f, I get that omega is equal to 2 pi f. Okay, so that's the first thing that comes out of the sinusoidal solution, and that is that omega must equal 2 pi times the linear frequency. We'll need that in a minute. Okay, the other thing is if you just look at that function there and you say, okay, let me fix t, so let me pretend that the time doesn't change, but let me just move along x. Okay, so that's like taking a snapshot in time. That's actually what you're seeing here. You take a look at a snapshot in time and you go, okay, how fast does this thing oscillate in space here, like that. And you know that I didn't draw this in here, but you know that the distance, let me do it in green because it's getting a little bit messy. You know that the distance from here, from crest to crest, is lambda, like that. Okay, and so that wave number k must be related to lambda, and here's how. Okay, so we fix time, so we're taking like a snapshot and we let x change, we let x vary, and since the cosine makes an oscillation in 2 pi, we must get that in distance x we've traveled one wavelength, and that means that k times lambda must equal 2 pi, or k is equal to 2 pi over lambda. Okay, now there isn't an equivalent of a frequency there, so we just leave that as 2 pi over lambda. Okay, and now what? Well, now we say, okay, does this function even solve that equation up there? Does it even solve it? And the answer is yes. So what we're going to do is we're going to take this and we're going to differentiate it. Okay, so let's differentiate it once with respect to time. Okay, so if you have this function here, all right, so that's not the answer right now. Okay, we have to differentiate it with respect to time. If we differentiate this function with respect to time, what do we get? Well, when a is a constant, so it just comes out front. The cosine, when you differentiate a cosine, you get a negative sign. Okay, so you get that. But you're not done, because that isn't just t, that's omega t. So when you differentiate that using the chain rule again, you get an extra omega out in front, like that. Okay, so there is the first derivative of that. The first derivative of the cosine is the negative sign. And because it's omega t, you get an extra omega out in front there, like that. Okay, now what? Well, let's differentiate this a second time. We'll differentiate it a second time with respect to time. And so we're starting from this now, because that's the first derivative. We differentiate it again. The derivative of the sine is cosine. Okay, and again, we're differentiating with respect to t, but that's omega t. And so you get an extra omega in front, and that gives you an omega squared here, like that. Okay, so there you go. There's the second derivative. Notice that this is equal to omega squared multiplied by a cosine omega t, but a cosine omega t is y all over again. And so once you differentiate it twice, you come back to y. And so we could just write y in there, like that. Okay, so there's the derivative, second derivative with respect to time. That's the left-hand side. That's like the acceleration of a point on the wave. Okay, one of the oscillators that make up the medium. What about differentiating it with respect to x? Okay, well, same function to start with, but now we differentiate this. When we differentiate the cosine, we get negative sine. So there's your first derivative. Okay, but again, you're differentiating with respect to x, not kx, and so this will bring an extra k out in front, like that. Okay, you might wonder, well, does it bring an extra negative in front? Not really, because it turns out that the cosine is actually a symmetrical function, meaning that this is the same as if I were to switch these around like that. If I were to just do that. In other words, if I multiply the argument of the cosine by a negative, it's the same thing, okay? So it doesn't matter that there's a negative there. That doesn't really affect anything, okay? So great, there's the first derivative, okay? And the second derivative now with respect to time, with respect to x, like that. If we differentiate this, okay, we're going to get another, the sign's going to become a cosine, and we're going to get another x in front like that. Sorry, another k in front, so we've got two k's here. And so this is going to equal negative k squared multiplied by y again. And so we get y back. Okay, great. So what? Well, let's go back to this. If we go back to that, okay, this quantity we can now write as this right here. See that d2y by dt squared? We can write that as that right there. Okay, so let's remove that, and let's put that in here like that. Okay, and then this one, we'll keep the brackets there. That's this one. All right, and there we go. So this equation here, when you replace the y with some sinusoidal function, okay, you'll get that. Okay, now let's simplify that. First thing you'll notice is that you can get rid of the negative sign on both sides. Okay, now we can get rid of those brackets. All right, it reduces that. The second thing you'll notice, there's a y on both sides. Now normally you have to be careful not to divide by 0. Remember, y is a function, so it works for all times and all positions in space, all values of t and all values of x. And so yeah, you can divide that out. So that then simplifies to this. And then it further simplifies because everything is squared here, and they're all positive numbers, okay? So you could just take the square root of everything, and ta-da, you get this equation. And you go, well, what is that? That is basically this equation, okay? This equation here is the angular form. Let me clean it up a bit. This equation here is the angular form of that equation, and which is the linear form. Okay, linear meaning in terms of linear quantities, and this one in terms of angular quantities. Okay, omega is an angular quantity, it's an angular velocity, and k is called a wave number, but it's kind of like an angular reciprocal wavelength. Okay, and the angular part means that there's just a 2 pi in there. So for omega, it's angular because there's a 2 pi in there. You can see it there, and also there. And k is also an angular quantity because there's a 2 pi there like that. Okay, now you could go through life just using that as instead of v is equal to lambda f, but it's kind of annoying to work in angular quantities. So let's see if we can replace the angular quantities with the linear, and if we get that equation there. Okay, so for omega we have this. Okay, whoops, no, not all of it, just this part right here. So omega is 2 pi f, so that omega there is 2 pi f, and that's going to equal v. And for the k there, I've got right here 2 pi over lambda, so it's 2 pi over lambda. Okay, divide both sides by 2 pi. All right, and then you get that. Multiply both sides by lambda, and you will get that v is equal to lambda f. And ta-da, so this equation here and that equation right there, they're really the same equation. Again, one is just the angular equivalent of the other. Okay, so what kind of questions could I ask? Well, I didn't actually formally ask the questions, but I kind of did ask the questions as I would ask them on the test. Okay, or as I will ask them on the test. Okay, one of them is going to be what is the relationship between omega and the period, and or what is the relationship between omega and the linear frequency. Okay, and it's not just enough to know the formula. You should know that that's because the cosine makes a period in 2 pi. Okay. I will also ask, what's the relationship between K and lambda? And again, it's important to know that this 2 pi in there is coming because the cosine has a periodicity of 2 pi. Okay. I could ask for the first derivative of y with respect to time. I can ask for the second derivative of y with respect to time. I can ask for the first derivative of x with respect to time, the second derivative of, second derivative of y with respect to x. Say that again. The first derivative of y with respect to x, the second derivative of y with respect to x, and then finally, that this equation emerges from that with that solution. Okay, and then of course using these, I could say using these show that that is the case. Okay, and well, there it is. Okay, so not a very long video, but I just wanted to, and I did go over this stuff before, but I just wanted to add this little extra addendum to make sure that you're very clear to the kinds of questions that I could ask. Okay, so maybe just one last thing, and then I could say something like this: given that the waves are described by the equation this. Okay, show that well, I don't know if I'd say show, because it's multiple choice, but I would say show that this is a solution. Okay, I wouldn't do a show that, but I would say show what is the first derivative of that, what is the second derivative of that, show that that is a solution. Solution, and that it leads to this equation right here. All right, so that's roughly the kind of question. I would unpack that in terms of multiple choice questions, but that's the kind of question that you should be able to answer for the test. Okay, a short little live stream, but there it is. If you have any questions about this, feel free to ask me during the evening office hours or email me. All right, bye-bye.